Okay, so this is one of the, I guess, catch-up lectures, or maybe covering material we didn't get a chance to do in the main lecture part. So before I dive into the problem we're going to talk about in this kind of mini video, let's just say what we were discussing last time. So last time we were kind of discussing things we can do with asymptotic series expansions. So let's suppose that I have some expansion for x, I've got some approximation with my function x, and I've got some approximation for my function y. How can we combine these things together? Now really what I can do is I can get my two things and I can add them together. So if I want to work out an approximation or an asymptotic series expansion for x plus y, I can get these two results and I can add them together. So one of the morals was we can get asymptotic series expansions and we can add them together and they're still perfectly valid. Okay, so I guess the question is, beyond them, what else could we do? What else could we be interested in? And we can get asymptotic series expansions and we can also multiply them. So not just adding, subtract, we can multiply them. So if I want to work out an approximation for x times y, I can just get my approximation for x, which is this expression, my approximation for y, which is this expression. And then if we just multiply the brackets how we normally do, we end up with this. So all I'm saying there is don't worry about multiplying asymptotic series expansions together. That's also fine. And then after we talked about multiplying, the next thing we said was we can also divide asymptotic series expansions. So if I want to calculate what x over y is, this is so long as y is not equal to 0. Okay, if it equals 0, you've got problems. And what we can do is we can get our asymptotic series for x, and we can divide it by asymptotic series for y. And this is also valid. Now, one of the things in this course is whenever you're dividing by something, and you're wanting to work out an asymptotic, and you wanted to work out the asymptotic series expansion of it, 99% of the time you're going to use the binomial theorem. Okay, we don't really like dividing. Dividing is tricky, but multiplying is good. Because when we divide, we really want to get our answer in terms of epsilon, epsilon squareds, etc. And when you divide, you can't really do that. So if you ever divide an asymptotic series expansion, as we're going to see shortly, we should normally use the binomial theorem to turn division into multiplication. So remember, division is bad, multiplication is good. And what was the final thing we talked about in that lecture? Well, we said that if I've got an asymptotic series, I can integrate it. So if I want to work out the integral of x of t dt, what I can do is I can integrate my asymptotic series, and that is also fine. So I shouldn't put equals there, I should put twiddle. Okay, so the moral was we can add and subtract, we can multiply, we can divide, and we can integrate some asymptotic series expansions. But there are a few things missing on this list that you might have expected to be there. And what we're going to do today is going to talk about things that we can't do to asymptotic series. Okay? So let's start off with. So let's suppose I've got a question, right? So let's suppose I've got f of x twiddles g of x as x tends to a. So I'm kind of saying g of x is an approximation for f of x. Does that mean, can we say that e to the f of x twiddles e to the g of x as x tends to a? So can we say this? So can we treat it like an equal sign? Can we just take an exponential on both sides? And the answer is going to be no, but with a bit of a caveat. Okay, so we cannot do this. But I don't like it when somebody just tells me we can't do this. So to figure this out, what we're going to do is we're going to look at an example and see what goes wrong if I take the exponential. Okay, and so let's start this off, and I'm going to look at an example, and I'm going to take f of x to be equal to, so over here, x squared over x minus 1. My question is, what does f of x twiddle as x tends to infinity? Right? So really, I'm just trying to figure out what my g of x is going to be. So let's have a look here. Let's have a look at this case. So I've got x squared over x minus 1. And really, my brain immediately, well, I guess you can think of this as this case, 1 over x minus 1. And really what I see is I've kind of got an asymptotic series at the bottom, right? I'm doing some dividing by stuff here. And I don't really like dividing. That's one of the rules of the course. So whenever we see division, we should think binomial theorem. And there are a few different ways of writing the binomial theorem, but essentially, all I like to think of it as is 1 over 1 minus epsilon, twiddles 1 plus epsilon squared, plus epsilon cubed. It's really nice and easy to remember as epsilon tends to 0. So that's our binomial theorem, is basically just using this. Now there's a bit of a problem here in this case, is we want to look as when x tends to infinity. So x is a big number, and this expansion only works when epsilon tends to 0, so it only works for a small number. So somehow I need to get a small number to appear in here. Whenever you get a large number, the way to make it small, to use your favourite properties, is to do 1 divided by it. So I can say this is the same as x times 1 over 1 minus x. And now the beauty of this is 1 over x is small. So we can neaten this up a little bit. So I've got x times, that cancels with that, 1 over 1 minus 1 over x, and this twiddles x times, because we can multiply asymptotic series expansions, so in this case my epsilon is 1 over x, so this lot just twiddles 1 plus 1 over x plus 1 over x squared, etc., as x tends to infinity. So this twiddles x plus 1. If I multiply this through, we get x plus 1 over x plus 1 over x squared, etc., as x tends to infinity. So normally when we do an asymptotic series expansion, we normally only use the first 1, 2 or 3 terms, right, as our approximation. So what I'm going to say here is, let's just use the first term. So I'm just going to say this. So let's say we can say x squared over x minus 1 twiddles x. Okay, if I'm just using the first term. We'll come back and talk about what happens if I use more terms later. Okay, so what I've done there is, what does f of x twiddle as x tends to infinity? And the answer is it twiddles x. So the leading order contribution, the main term, is just x. Okay, so how can we apply it to this problem? So we've got, let's just go across here, let's adding a new page. So we've got f of x is x squared over x minus 1, and this twiddles x, and I'm going to set this to be my g of x as x tends to infinity. And remember, the question we're asking is, does e to the x squared over x minus 1 twiddle e to the x as x tends to infinity? Can I take an exponential on both sides of here? And to answer this question, we kind of need to remember what this twiddles means. We go to our formal definition, right? So our formal definition, if we can remember it, is, let's use some letters. So we say that we say h of x twiddles big H of x as x tends to a. Then all of this is always about these limits, right? then the limit as x tends to a of h of x divided by big H of x, the limit for the asymptotics case was 1. Right? So really, to answer this problem, what I need to do is calculate this limit. And before we do this, I'm going to get so our goal is to calculate this limit, but before we do this, let's remember that e to the x squared over x minus 1. I'm going to use the word equals here in a bit of a loose sense. What we're going to do is we're going to get this thing and we're going to replace it by all of the terms. So if we have all of the terms, it is exact. So here I'm going to get x plus 1 over x plus 1 over x squared plus dot 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 dot. Okay. So I'm being a little bit loose here in this, but I'm just going to say that those two things are equal. So what I can do now I've got this as the case, then the limit as x tends to infinity of e to the x squared over x minus 1 divided by e to the x must be equal to the limit as x tends to infinity of e to the x plus 1 over x plus 1 over x squared divided by e to the x. And now these first parts are going to cancel, right? I guess you can write this as e to the x times by e to the 1 plus 1 over x e to the x. Now these two parts are just going to cancel. And when we take this limit, we end up getting e to the 1 plus 0 plus 0 plus 0, which is e to the 1, which is about 2.7. So, why has this worked? Well, what's gone on here? Are they asymptotic? Well, if they are asymptotic, what should the limit be? The limit should be 1, right? Our definition of asymptotic says the limit's 1. But in our case, we've worked out the limit, and it's 2.7. So, as the limit, as x tends to infinity, of e to the x squared over x minus 1, divided by e to the x equals 2.7, which is not equal to 1, we say they're not asymptotics to each other. Does not twiddle e to the x as x tends to infinity. So the moral I'm trying to get across here is we should be careful when taking exponents or exponentials of asymptotic relations. We can't just necessarily take an exponential, it destroys it. And there are some questions in the tutorial about taking logarithms and taking sines and taking cos, which also shows us problems if you use those functions as well. But this isn't quite the end of the story. So sometimes we can take exponentials of asymptotic relations. We just need to be careful. So to see when this works, sorry, let me just delete this. So to see when we can do this, let's just go back to our first page here. And we said that the whole series, the whole asymptotic series was this. And we just used the first term. We just used the first term x. Well, what happens if I use the next term? So let's just write this down. So x squared over x plus 1 twiddles x plus 1 as x tends to infinity, right? I can choose where I want to stop my series. And let's suppose I want the next one. I want it to be a bit more accurate. A little bit more accurate. And it turns out, I'll let you do the maths if you want. Do the limit. We can say e to the x squared over x plus 1 twiddles e to the x plus 1 as x tends to infinity. So if we just use the first term, it doesn't work, but if you want to go through the mathematics, the idea, if you want to know, is we'd have a plus 1 here, we'd have a plus 1 here, that would cancel the 1, and we'd end up with a 1. Okay, but I'll let you go through that if you want to. But if we take the first two terms, then it does work. So maybe there's some sort of rule about taking the first two terms. Well, not quite that, but the rule basically says, so we say we can take exp of an asymptotic relation. So this could be an asymptotic series expansion if the, I'm going to call them leftover terms, the leftover terms tend to 0 in the limit. Okay, so let's have a look at what went wrong in this first case. So the first case we said x squared over x plus 1 twiddles x as x tends to infinity. And let's just remind ourselves of the full expansion. If I have infinitely many terms, if I want to keep all of the terms, which is impossible to do if you actually want to use it, but anyway, we've got this. So if this is the case, the leftover terms so let's have a look at our leftover terms. So our leftover terms, we could do x squared over x plus 1 minus x. And our leftover terms are 1 plus 1 over x, 1 over x squared plus 1 over x cubed. So these are all the bits we ignored, right? We ignored this bit and we just took this bit. And in the limit, as x tends to infinity, this tends to 1 plus 0 plus 0 plus 0, which is 1. Now our rule says we can take the exponential of an asymptotic relation if the leftover terms tend to 0. But our leftover terms are tending to 1. So that's the problem. Now what happens if we add on a plus 1? X plus 1 as x tends to infinity. So if that's the case, then our leftover terms, so I can just subtract the first bit on to see what's left over. Our leftover terms, so if we've used this one and this one, our leftover terms are just this thing. It's 1 over x plus 1 over x squared. These are the bits we're ignoring. And this does tend to 0 as x tends to infinity. So our leftover terms do tend to 0, so we can take the exponential. So we can say I'm going to write e there, twiddles e to the x plus 1. So we can take exponentials of asymptotic series relations, we just have to be careful about the bit we're ignoring. If you really want to write this as a theorem, it is in the lecture notes just written out. So it says suppose f of x equals g of x plus h of x, and f of x twiddles g of x as x tends to a. So this h of x basically represents the leftover terms, and all we can say is, well, what we can say is if h of x tends to 0 as x tends to a, or another way of writing this is to say h of x equals little o1 as x tends to a. I'll let you think about why this is true. These two statements are equivalent, they're both basically saying the same thing. Then we can take exponents. then we can say e to the f of x twiddles e to the g of x as x tends to a. And later on we're going to do something when we're looking at some waves, and which is something in mechanics, something called the WKB method, and this is going to be very important then. But the moral of this kind of story is we should be careful when taking exponents of asymptotic relations. It's not impossible, we just need to think about it first. Okay, that ends this video.